Okay, now let's talk about the test. So, as I said before, so the chapter quiz will be the problems in the quiz will be similar to the homework problem. It's not going to be exactly like the problem on the homework list. It's going to be changed, slightly changed, similar. And also, it's going to be some problem related to the example I show you in the class notes during the class time. So I'm going to go through some of these problems and help you to review. Now, one basic thing, you need to understand everything which has been covered by chapter 1, okay? So here, just remind you a couple of homework problems like number 2, okay? Number 2, showing that the subset containing, if a subset contains upper bound, then this upper bound has to be supremum of S. So problem like this, it will be a good problem for the quiz. Okay. Now here in this during the class, I actually have shown you the detailed proof. So this is the homework number 2, and also problem like the homework number 3. Okay, number 3. So you are dealing with a subset, and then you can establish relationship between these lower bound, the infimum and supremum. All right. So I will continue to look at the other problems like, okay, go to 79. Okay, so remember what we talked about the Archimedean properties, and we also mentioned some similar result like this one. So given x in R, we want to find, instead of an integer, now we want to find a rational number greater than x, okay? So the proof can be done using exactly the same argument as we did in the for the Archimedean proof, okay? And also problem like the other one, suppose you want to control the x by an irrational number, the same kind of proof. And also I indicated that the difference of these proofs. Now, if I want you, suppose I have a similar problem. If I ask you to handle this from beginning without using the Archimedean property, that you can proceed in this way, okay? Now, if I ask you to prove things like that using Archimedean property, then you should not go through this way. I mean, you have used the result, the Archimedean proof, to establish the new result, which I'm going to show you in a minute. So let's consider like this. So this is a proof for the existence of square root 2, right? The proof of existence of square root 2. So here you can see the paragraph in color red. It says that so that's the key argument. It says by Archimedean property, so there exists the integer m, so that xn less than m, so that x is less than m log n. So this is a proof using Archimedean property to get a new result. The new result is that for any x, there is a fraction controlling x. Okay, so this means that there is an existence of a rational number control x, right? Okay, and so you can see then, and in that case, I actually revisit the same problem. I showing you that the previous result showing the existence of rational number control any x can be done in this way. I mean, if I ask you to use the Archimedean proof to establish this result, and you have to use this argument. Okay, you choose any n, then you can use directly the Archimedean property to claim the existence of m over n. Okay, so a problem like this is important. Okay, and let's also visit the one of the difficult proof in this chapter is the existence of square root 2, right? So So this theorem is important. Of course, I'm not asking you to write copy or write a long proof like this, okay? But you need to understand the details of every steps of these proofs, okay? And maybe I'm asking you to use your own language to describe some of these proofs, okay? You have to prepare in this way. So the best way to prepare is to review this proof. Understand every detail, right? Okay, now let's move on to 106. And the last things we talk about in this chapter is about the nested cells property, okay? So when we say about nested cells property, we have a theorem, as basically nested cell theorem, and together with this corollary. So this corollary basically indicates that the intersection of this Rn is exactly equals to this closed interval C and eta. So that's the result. And in the proof, you can use this result. Okay, maybe I will ask you to prove a part of it, but you can actually use this to prove something new. Okay, and actually I mentioned this during the class that if this Rn thing, if the interval An to Bn, I mean, shrink to a point, and what can you say? Then we'll see that the intersection will consist only one point, right? The intersection will consist only one point. And how to prove it? You may think about it, all right? Okay, so these are the hint for you to prepare for this chapter quiz, okay? And so I'm going to have a detailed description of the test, maybe tomorrow. I will send this information to the class and how this can be arranged. It's mostly like it's something like this. So the test, so before the test, I mean, like 3:45, something like this, I'm going to email, I'm going to announce the problem through Blackboard. Okay, so everyone will see the problems. And then you can start to, the test will start at 4 o'clock and it should be finished by, you have the whole class time to finish everything. So after you finished, so you have to upload your test to the Blackboard by 5:30. All right, so this is my arrangement. Do you have any questions?
So we won't have like a Zoom call that day. We'll just do the test on our
No.
right?
We're going to have a Zoom session, and also I'm going to shoot the test during the Zoom. In the Zoom.
Okay.
Yeah. So if anyone can have questions, so I can answer through the Zoom.
Okay. Awesome. Thank you.
Okay. Other questions? Okay. So we're going to. I'm going to communicate more about this test later. Yeah.
I had a question. Can we use our notes during the test?
Oh yeah, it's an open book test. Okay, you can read the notes. Yeah.
Thank you.
Okay. Okay, so I'm going to start sharing this, and then I begin to. Hold on just a second. Okay. Begin to. Now let's begin about the chapter 2. Okay.
Hello. Is this room 108? Okay. I think Jackie, she was trying to call you, but I was not able to transfer her to your room. So can you hold
I can't hear you clearly. Could you? And what's the question is? Okay. Now, if anyone have any questions regarding the lecture and the coming quiz, and we can talk about this during the office hour. Okay. me see. Okay, so now let's begin the chapter 2, okay. Now, so we are now entering chapter 2. Now, chapter 2 is about the limit of sequence, okay. So we talk about, from 415, you have already understand what I mean by sequence, and also you know what is limit, but we are going to study more theorem about the sequence limit, okay? So we begin with a very general definition. So this is basically copy from 415 for the first few slides. Okay, so we, so suppose we have a sequence. What does it mean is you have a sequence of real numbers. It's A1, A2 to AN. And so the general term AN is normally given by formula, like AN is given by like N squared. N squared denotes a sequence, like 1, 4, 9. N squared is a perfect sequence, right? Perfect square sequence. Okay, so that's one of the examples, okay? The second example is that you can have, so when you talk about sequence, you can have all different kind of sequence. Here I'm choosing some, typical sequence and to show you. So the second sequence is -1 to the n is the power. So then you can see this sequence represent the real number, just -1 and 1, -1, alternate in this way, right? Then number 3 is a sequence given by a fraction, n over n plus 1. So this sequence represents 1/2, 2/3, and 3/4, and so on. Now, if you look at this sequence, so why we want to study sequence? Sequences have all different kind of sequence, right? But we want to study behavior of the sequence. Especially, we want to study those sequences behave nicely that carries a limit, okay? Now, if you look at the first sequence, so first, all these sequences can be considered as a function, okay, in some sense. So it can be considered as function from integer set to the real number set R. So Fn equals n, that means n is mapped to the an. So we can use a function, a language of function to describe the sequence. Okay, so now let's look at this behavior of the sequence, okay? Now, the first sequence, you can see the sequence goes to the infinity because that's a perfect square. So as n goes to infinity, so n squared will suddenly goes to plus infinity. It goes to infinity. So this sequence is unbounded, okay? And it just goes to the infinity. And second sequence is -1 to n, and this sequence obviously is bounded, but however, it goes nowhere because it's vary from -1 to 1, okay? This goes nowhere. But the third sequence is a nice sequence, and those sequences we want to talk about it.
Hello.
Yes. Hello?
Well, what's wrong?
My receipt for my room,
Which room is that?
Any questions?
room 105.
Excuse me? Okay, anyway, okay. Now, the third sequence is a nice behaved sequence because this sequence carries what we call limit. Because think about 1/2, 2/3, and those sequence, n over n eventually will go to 1. Okay, the sequence will approach to a fixed number. So these are the sequences we want to look at in detail. It's nice behaved, okay? So in this case, 1 is called a limit of the sequence, n over n. Or we can say that this sequence converges to 1. Okay, so here we want to just develop this limit concept to a general sequence. So let's see how we can define a limit. Okay. Now, as I said before, I mean, the sequence can be considered as a function. So for a function, you can look at a graph. So if you look at the graph, controlled by, given by the example 3, for instance. So the sequence will gradually increase to a certain number R, to a number L. L is actually the limit of sequence, okay? Okay, so now we are in a position to define the limit. So here is 2.1 is a definition, okay? So let's say that you have a xn is a sequence of real number. And then you have an x here, x in R is also a real number. Now, what does it mean that xn will approach to x? What does it mean? So this means that generally it says that xn the value of turn will goes to x, right? But mathematically, this needs to be defined in a very careful way, okay? And this definition is done in 415. Now I'm here review this definition with you. So we say xn converge to x, or we say that xn has a limit x, which is written by limit xn equal x, if only if the following condition hold. So the condition is written by epsilon k language. So if only if what? If only if for every epsilon is considered as a small positive number, okay? For every epsilon, there exists a positive integer k such that when n greater than k, then xn minus x, the distance will be less than epsilon. So if this is satisfied for every epsilon, then we say that the limit xn is equal to x. So mathematically, we have to define the limit using this way. That's the only way you can define the limit, okay? So here is some follow-up definition. So if xn has a limit, then we say that xn is convergent, okay? So for instance, in the previous example, example number three has a limit 1. So therefore, the sequence number 3 is converging. And the other two sequences, number 1 and number 2, they are not converging. So when a sequence has no limit, then we say that the xn is divergent. Okay, so that's the limit concept, okay? Now, at the beginning of this chapter, so first we want to understand completely this definition, and also we need to learn how to apply this definition to verify the limit of certain sequence, okay? Now, here is a graph, and you can see what exactly mean by the epsilon k argument, okay? So in this graph, you can see the middle line. The A is supposed to be a limit of a sequence. So given epsilon, meaning that you're giving a narrow strip for this x, okay? So this means that when n large enough, and this term will eventually lie inside this strip. Okay, so that's the, using graph, you can understand the epsilon k argument in this way. Okay, so here we are going to see a number of sequence, number of the examples, okay? And the first example is actually similar to the example we have learned from the 415 already. So we have a sequence, 2n minus 3 over 3n plus 1. We want to show that this limit equals to 2/3, okay? Now, actually at the beginning, you have to do some analysis, okay, for this. We have to do some computation before we can write down the formal proof of this. Now remember, so in order to verify this limit, basically you need to solve an inequality. So you take the term 2n minus 3 over 3n plus 1 minus the 2/3, okay? You look at absolute value of this difference. And you want to show that when n large enough, this difference is less than any given epsilon. Okay, so epsilon is given here. Okay, so how do I know that this will eventually be satisfied if n is large enough? You have to show me the k. Okay, so that's the, to prove these things, you need to basically solve this inequality to display the k. So here we are doing some analysis, okay? Now, in order for the difference, now the difference can be written as 11 over 3 times 3n plus 1, okay? That's the difference. Now you want to show the difference less epsilon. This means that you want to solve this inequality. 11 over 3 times 3n plus 1 less than epsilon. Now this inequality can be solved easily because you can flip the inequality and then you can find out that as long as n greater than 1/9 times 11 over epsilon minus 3, then this inequality will be satisfied. So this tells us that when n greater than this, we will have the desired result. That's the difference between the term and the limit is less than epsilon, right? So this tells us that if I can choose k, if I choose k to be any integer greater than this number, then when n is greater than k, then of course this condition will be satisfied, then you will have the desired result. Okay, so this is the analysis. You can work on this analysis on a piece of paper. Now, once you understand this, and then you can write down the formal proof. Okay, so here for the first few examples of limit, we always do some analysis like this, help you to understand the detailed proof, okay? Now, with this, keep this in mind. So now you can write down the proof. The formal writing of proof is that you begin with an arbitrary epsilon. So for any epsilon greater than 0, so based on the previous calculation, I know that how I can choose a k. So once epsilon given, you just pick a k. So you can say I choose the k, integer k, such that k is greater than this fixed number. Okay, though obviously there's lots of k like this. I don't care. We don't care whether the k is smallest one set like this or what. As long as you have a k like this, it will be sufficient. So given an epsilon, I simply pick a k greater than this number. And then you see that for n greater than k, and we're going to have n is greater than 1/9 over 11 over epsilon minus 3. Okay, and then you basically you're going backwards. I mean, the backwards of the previous calculation. And this inequality where n is greater than this, and this will imply that 11 over 3 times 3n plus 1 is less than epsilon. And therefore, you can go to the final inequality. So the difference between term with the limit, which is equal to 11 over 3 times 3n plus 1, will be less than epsilon. So that's the formal writing of the proof. So you begin with epsilon, then you choose k. Now, how do you choose k? You actually based on your preparation, basic analysis. And then from this k, you want to verify that the final inequality is satisfied as long as n greater than k. So that's the writing of the proof for this limit. Okay. So this is a very simple numerical example. So here, we want to continue to look at some more challenging example. Okay. So the next example is still similar to the one is given by the Math 415. So in this example, we want to show that the difference between, so the sequence is square root n plus 1 minus square root n minus 3. So this is the sequence. We want to show that this sequence goes to 0. Okay. So this means we want to show that the limit is equal to 0. Now how we can do that? And so again, we do some analysis. Okay. So we want this term minus the limit 0, right? Is less than epsilon. But we need to look at this difference first. So square root n plus 1 minus square root n minus 1 minus 0, putting absolute value sign outside. Now this is precisely equal to square root n plus 1 minus square root n minus 1. Okay. Then here you need to use some algebraic manipulation. This turns out to be equal to 2 over square root n plus 1 plus square root n minus 1. Now why? Because we remember formula. Now if you have square root a minus square root b, okay, this is always equal to a minus b divided by square root a plus square root b. So this is a very basic algebraic formula. Okay, so you use this formula to simplify your expression, and this is a necessary step. Okay, and now you can see your ultimate goal is to show that when n large enough, square root n plus 1 minus square root n minus 1 minus 0 is less than epsilon. Now this inequality, this final inequality now is equivalent to what? Equivalent to the new inequality, which is 2 over square root n plus 1 plus square root n minus 1 is less than epsilon. Okay, so now we can work on this new inequality to see, to find out what will be your k. So, but however, solving this inequality is not easy because you have a double square root sign there. So in order to solve the inequality, you need to simplify it first, okay? Now simplification is very simple because the whole thing is less than square root or less than 2 over square root n. Okay. Now why this is true? I mean, every time you have when you solve inequality, you want to try to simplify it, okay? Because this simplification will give us, okay, because suppose this is true, then the original inequality is now reduced to 2 over square root n less than epsilon, which is very simplified, okay? Now the question is why this is true? This is true is because that the, you remember, the square root n plus 1 plus square root n minus 1, this summation is greater than square root n, okay? So therefore, if you take the reciprocal of these, you will get this inequality immediately, okay? So in order to find your solution, 2 over square root n plus 1 plus square root n minus 1 less than epsilon, now you can solve it by a much simplified inequality. 2 over n square root n less than epsilon. And this one has a very nice solution, n greater than, the solution is n greater than 1 over 4 epsilon squared. So that means when n greater than this, then you will have that 2 over square root n is less than epsilon, and therefore you will have the original inequality hold. Okay, so this means that you need to choose k, and to be any integer greater than 1 over 4 epsilon squared. And then you will be able to get the final inequality to get a proof done. Okay. Okay, based on this idea, so now you can write down the proof. So to write a proof, so again, you start with epsilon for any epsilon greater than 0. Then you choose k such that k is greater than this number, 1 over 4 epsilon squared. Okay, and then you can see for any k greater than k, for any n greater than k, you're going to have n is greater than 1 over 4 epsilon squared, and this will, I mean, you're going backwards of the, the inequality in the previous step. You'll see that this will imply 2 over square root n is less than epsilon, and that's all we need. So because this inequality will imply the final inequality. So then we are going to have that the final inequality, so square root n plus 1 minus square root n minus 1, this things, which is equal to 2 over that, is less than 2 over square root n is less than epsilon. And so therefore this is proved. Okay. So this is so this for this limit, you can see that at the very beginning we have use an algebraic manipulation to change this. Otherwise, it will be difficult, okay, to prove it. All right, so this is number 2. Okay, so the number 1, number 2, they are basically example from Math 415. Now we are going to see some new examples, okay? Now, the next example, number 4, or number 3, we are going to show that here you have b. B is a number between 0 and 1, it's a positive number. And you look at the n's power of b, okay? Then you let n goes to infinity. So you can see that the bn supposedly goes to 0, right? The limit should be 0. And now here we are going to try to prove this result using the epsilon k argument, okay? Now how we can prove this? So let's do some analysis. Okay, the final inequality is very simple. You want to just show that bn is less than epsilon. Okay, now in order to do that, you have to use log on both sides. You take a natural log on both sides. So that's the log based on e, the base e, okay? Take a log on both sides. Then the left side, then log bn equals to n times log b, okay, the power rule. Okay, the right side is log epsilon. So now you can see you can easily solve this inequality. So you can see that this inequality is equivalent to n is greater than log epsilon over log b. So basically, we divide the log b on both sides of the previous inequality. Okay, but remember that the log b is between 0 and 1, and b is smaller than 1. So log b is negative. Okay, so if you divide the log b, you are dividing a negative number, so inequality sign changed. So that's why you get n is greater than log epsilon divided by log b. Okay. And so this, from here, you can see easily find the k. K has to be any integer greater than log epsilon over log b, right? So you can immediately, you can begin right on the proof. Okay, so for any epsilon greater than 0, you choose k. K is greater than log epsilon and over log b. And then you can see for n greater than k, we have n will be greater than log epsilon log b. Then from here, you can going backwards. You can see this will implies n times log b less than log epsilon. And again, you remember this time you multiply log b on that inequality, and you multiplying a negative number, so inequality sign change, and this simply implies that bn over epsilon. Because you put n back to the exponents, and they take away log on both sides, you'll get this. So that's the proof. It is very short. The proof is very short. Okay. Okay, so now we are going to continue to see some other examples. Other example, the next one will be like this. And C is here you have a constant C. C is a positive number, real number, okay? It's positive number. And then the power here, the sequence is C of 1 over n. The power is 1 over n, okay? So then you take a limit, and we want to show that this limit equals 1. Okay, there's some. Okay, there are people asking question for the second example of 2a. I understand why it is greater than the original limit, but why is less than epsilon? Okay, so let's go back to here to talk about this. Okay. I'm moving to here. Okay, so in the proof that, maybe we have to go back to the previous slides. No, we can. So here, for every given epsilon, so epsilon is given, okay, and we choose the k is greater than this number. So k is greater than 1 over 4 epsilon squared. Okay, and now for every n greater than k, obviously the n will also greater than 1 over 4 epsilon squared. Okay, and then from here, this inequality will imply that 2 over square root n is less than epsilon, because this is the backwards of the previous calculation. Okay, and you can, for instance, like you multiply. Let me see. Did I do something? Okay, so maybe there's okay, the 4 is on the denominator, not in the top, not in bottom. I mean, so let us check, okay? Check from the previous calculation. Yeah, okay. The 4 is, sorry, there's a typo here. The 4 has to be, you're right. The 4 has to be on the top, okay? So that means 4 over epsilon squared, not the 1 over 4 epsilon squared. And then you can see that it will solve the problem, okay? So this means that the we choose the k greater than 4 over epsilon squared. And then from here, and you are going to get the result, 2 over n square root n is less than, yeah, okay, it's very good, okay. Yes, that's the problems, yeah, we have to fix it. Okay, all right, so this is the, so we have already done the number 3. So now let's move on to the number 4, okay. So this one is slightly different. Now here, C is a constant, okay, and the power is 1 over n. Then we take a limit, let n goes to infinity. Now, from this expression, you can, obviously you will believe that the limit is equal to 1 because 1 over n will goes to 0. So the 0 power of every real number is exactly equal to 1. Okay, so, but however, we need to give a proof. Now, starting from this example, I'm not going to do the analysis. Okay, I just begin to the beginning to the end. I'm going to write the proof directly. Okay, so we need to divide into 2 cases. Okay, the case 1. Let's assume now when c equals 1, then obviously this result hold because when c equals 1, then 1 to any power equals 1. So the sequence becomes a constant sequence. And so the limit obviously is equal to 1. So let's divide it into 2 cases. The case 1 is c is less than 1, but c is greater than 0, okay? Now in order to give a proof, we need to do some preparation of that, okay? And what we need to do is that in this case, we observe that c to the 1 over n is less than 1. Okay, the sequence is always less than 1. Therefore, I can rewrite this term, c over 1 over n. We can set the c to the 1 over n to be 1 over 1 plus bn, with bn greater than 0. So this is a setting, basically this is a setting. So this means that this is just because that our sequence is less than 1. So I can re-express the sequence as another sequence bn in this formula. Because 1 over 1 plus bn is always less than 1. So this bn is well defined in this case, okay? It's well defined. So instead of working with the origin sequence, now let's work on the bn. You think about it, if you want to choose c of 1 over n goes to 0 or goes to 1, you need to choose that bn goes to 0. That means if you can choose bn goes to 0, then of course this original sequence goes to 1, right? Okay. So then from this expression, you can see that I take the reciprocal of that, and I take the reciprocal on both sides of this equality, and then take n's power. You apply the n's power to it. So put n's power to it, then you can eliminate 1 over n in the exponent. Okay, so you will get the 1 over c equals to 1 plus bn to n's power. Okay, so I do the manipulation in such a way. Okay, you have a new expression here. So here, since c is a constant, okay, so 1 over c is just a constant. Okay, the 1 over c happens to be 1 plus bn to the n. No matter what n you choose, this power is always equal to 1 over c. Now, the next, we are going to show that, and this is greater than bn. Okay, greater than bn. Now, why? I didn't show the reason, but in the actual proof, you can write this down because there is a formula behind this. Now, the formula is that you think about the binomial expansion. Okay, binomial expansion like the formula like 1 plus a to the n can be expanded to be 1 plus n times a, then plus many other terms. Okay, so there's an explain tell you what all these terms are exactly is. Okay, but when you then will apply this binomial expansion, then you can see the 1 plus bn to the n's power. Now it's going to be equals to 1 plus nbn. The nbn will be the second term, and then there will be some other term after that, right? But at this time, we don't care about the other term because every term in this expansion are positive, okay? So therefore, I just take one of these terms, so that means the summation will get smaller. So that's how I get inequality. That's 1 plus bn to the n's power is greater than, simply greater than bn. Of course, I can insert additional term to it on the right side. I can put a second term there, but it's not necessary. We don't want to. So I just take one term there. So this will tell us that once I setting the whole expression like that, I will have that 1 over c, the 1 over c is always greater than n times bn. Okay, 1 over c is always greater than n times bn. So this will imply that the bn is less than 1 over cn. Okay, so this is the key result. So from this result, you can easily see that the bn is actually goes to 0. Because when n goes to the infinity, 1 over n will go to 0. And c is a constant here. Okay, now we know how to continue next step. So actually in the proof, we need 1 over cn is less than epsilon. Okay, now anyway, so this paragraph should be included in the proof, okay? It's a preparation. So prepare us to prove that the bn goes to 0. So in the next paragraph, we want to just show that bn goes to 0 using this epsilon k argument, okay? Now for every epsilon greater than 0, now I simply choose the k is greater than, okay, so what the k has to be. K has to be any integer greater than 1 over c epsilon. This is coming from the previous inequality, right? So therefore, when n is greater than k, you will have n is greater than 1 over c epsilon, which implies that 1 over c over n is less than epsilon. And therefore, this implies that the bn is less than what? B to the n, okay, is less than epsilon. No, so sorry, there's another typo, okay. This simply means that the bn is less than epsilon, not the b to the n's power, okay. And then you can work on the previous inequality, the following inequality. The following inequality should start from c to the 1 over n minus 1, right? You want to choose that this difference is less than epsilon. Okay, so then you have to work for several steps to reach that. Now first, then c to the 1 over n minus 1, okay, based on our expression, this basically equals to 1 over 1 plus n minus 1, okay, based on our setting. And therefore, if you just make a subtraction between 1 over 1 plus bn minus 1, so this will equals to the bn over 1 plus bn. Okay, and this expression can be simplified because the bottom part is 1 plus bn is greater than 1. This because bn is greater than 0. So therefore, the bn over 1 plus bn is less than bn. And now we know that bn is less than epsilon. So therefore, this implies that the following inequality hold. That is, c 1 over n minus 1 is less than epsilon. That's how we finish the proof. Okay, so this is the so this problem is kind of special, and so you have to make some setting, okay, and manipulation before you can get to the key step of the proof. So that's case 1. So now let's look at the case 2. Case 2 is c greater than equal to 1. So let's say that c is greater than 1. Greater than 1. Because equal 1 case, it's simple. They are just constants. Okay. So when c c to the 1 over n is greater than 1, okay, but you can include it equal case, okay. Now we are going to have another setting. I'm going to set the 1 over cn, c to the 1 over n now is equal 1 plus the bn. Okay, so because it's greater than 1, so we don't need to have a fraction, just 1 plus bn, and with bn is greater than 0. And now we're going to show that the bn goes to 0. Okay, again, we'll follow similar steps to do this, okay? Now how we can do this? So again, we put the n's power on both sides, okay? So you get c to the 1 plus bn to the n's power, okay? C is always equal to this expression. And then this expression, 1 plus bn to the n's power, is always greater than n to bn because of the same reason as in the previous case. So this basically means that the bn, so you can see in this case, it's simpler than the previous case. So from here, you can simply see that, okay, that bn is less or equal than c over n, okay? So that's sufficient for us to show that bn goes to 0, okay? So for any given epsilon, and choose k greater than this number, and then when n greater than k, and you can see that the n will automatically greater than c over epsilon, okay? And that's what implies that c over n is less than epsilon, which implies, now again, there's a typo. I will fix later. So b sub n is less than epsilon. And then you can see the c to the 1 over n minus 1, this final inequality turn exactly equal to bn, okay? Because it's a 1 plus bn minus 1. It's exactly bn. It's less than epsilon. So therefore it is satisfied. So that's the proof of the case 2, the case 2 proof. So do we have any questions? If no questions, we are going to finish with the last example. Last example is slightly different, okay? So the next example is we're going to look at the sequence n to the power of 1 over n. Again, we're going to show that this is equal to 1. Now previously, the n, the regular n is replaced. Now you can see it's a constant. Now this time it's replaced by n. So this sequence is bigger than the previous two, okay? And then we're going to still show that the limit is still equal 1, okay? Surprisingly, the limit is still equal 1, okay? Now this is a non-trivial result, okay? And we're trying to prove this using the same argument for the previous two examples. And we know that n to the 1 over n is greater than, okay, there's some other comments. Let me see. Why c to the 1 over n is equal to 1 over 1 plus bn, where c is less than 1. Okay, when c is less than 1, then you can see c to the any power. C to the any power is less than 1. So c to the power of 1 over n is something smaller than 1. Now, if you have something smaller than 1, so that number can be expressed by 1 over something, which the bottom number is greater than 1. So because this fraction will be smaller than 1. So you can always define bn to be a positive sequence so that 1 over 1 plus bn is exactly equal to c over 1 over n. Okay, so the reason is because that the when c is between 0 and 1, then c to the power of 1 over n is smaller than 1. Okay, so that's the reason, right? Okay, so let's continue here. So in this case, you can see n to the 1 over n power. Okay, this is always greater equal than 1. Always greater equal than 1. Okay, so as in the previous case, you can set the 1 over, you can set n to the 1 over n and equals to just 1 plus bn with some bn greater than 0. Okay, in exactly the same way, right? In the previous case. And so the bn's were defined. Now we're going to show that bn goes to 0. The question is, how come this case Bn still goes to 0? So we're trying to continue, okay? Okay, and then we going to do the same thing. We take n's power on both sides. You have n equals to 1 plus Bn to n's power. Okay, now, so we are proceed in the same way as we did in the case 2, right? But in the next step, we're doing something different. Now remember this expansion. Remember this expansion. 1 plus a to the n. You have many terms. This time, I'm not choosing the second term. I'm choosing the third term on the right side. The reason I'm choosing third term because in the third term, you have 2n there. You have product of n. Okay. If you choose a second, still choosing second, then you have only 1n. That's insufficient in this new case because you know that on the left side of this inequality, you exactly have 1n there. Previously, it's a constant. Now the left side is an n here. So this n needs to be canceled by some n on the right side. So if you have that only 1n on the right side is sufficient, is insufficient. So that's why we choose the third term, which is n times n minus 1 divided by 2, the a squared. In this case, it's a bn squared. To continue. And then you can see that the n canceled, n can be canceled, then the bn still can be controlled by something small. Okay. And then you can see this will imply that the bn is less than square root 2 over n minus 1. Of course, the expression is a little bit complicated. You see, the n canceled, okay? The n canceled, so you can see, so on the left side is exactly 1, okay? The right side is, you have a square on the bn, and also you have n minus 1 divided by 2. So you divide this number to the other side, you get 2 over n minus 1. Then you take a square root. You take a square root. So therefore you get bn now is less or equal than square root 2 over n minus 1. So that's a new control by bn in this new case. Now if you just using the second term, like a b, okay, suppose you just use the second term. The second term will be just the n to the bn, that's it. Then you can see n canceled. So what you get is bn is less than 1. Is bn less than 1. From which you cannot prove that bn goes to 0. Okay. Now, because of where you the third term, so you can see that the bn is controlled by something, you will still have n on the denominator. That thing will go to 0. So that's the reason why we picked the new term here. Okay, so now you can see in order to prove the final inequality, we need this to be less than epsilon. Okay, square root 2 over n minus 1 is less than epsilon. So now you can begin the paragraph, the key paragraph. So for any epsilon greater than 0, you just choose k such with the k is greater than I mean, here I didn't put additional detail. I mean, when you solve the inequality, previous inequality, square root 2 over n minus 1 less than epsilon, you're going to get n has to be greater than 2 over epsilon squared plus 1. Because you square it on both sides. Square it on both sides. And then you divide by 2. Okay? Then take the reciprocal. Then you put minus 1 to the other side, you'll get this inequality. So that's a requirement for the k, okay? So for any given epsilon, you choose k is greater than this number. And then when n is greater than k, you will have n is also greater than this number. And this will imply that 2 over the square root 2 over n minus 1 is less than epsilon, which will give you bn less than epsilon. And finally, you can write that, therefore, so the n to the power 1 over n minus 1, which is equal to 1 plus bn minus 1, which is equal to bn, is less than epsilon. And then this is proven. Then this is proved. Okay, so that's a proof of this inequality. So so here we have been talking about a couple of examples. Okay, the last three example is a new example to you, to most of you. Okay, so you have to spend time to review these arguments. Okay. Okay, so this is all I have to say today, and I would like to also assign some homework problems. Okay, so let me stop sharing this one. So let's look at the lecture notes. And if you look at lecture notes, so in the end of the lecture note, there are exercise, right? So I would like to assign number 1 and number 2. Now, number 1 is very simple. It's like a numerical example, just like the example 1, okay? And number two is also simple, but it's slightly different. The number 2 is something related to the last example we just talked about. Instead of n to the 1 over n, now I'm having a 1 plus 2n. I have 1 plus 2n in place of n. Then the power of 1 over n. We want to show that this limit also equal 1. Okay, so these are the 2 examples I assigned today. So after the test on Thursday, you should work on these 2 examples. I'm going to come back to these 2 examples later in the next week, before I move on to other things. All right. Any questions? Okay, so no questions, so we can finish today now. Okay, we can have office hour in maybe 15 minutes, right? Okay, thank you.
Have a good day.
Okay.